I'm happy to introduce our next speaker and co-organizer, Aman Gupta, who's a postdoc at Stanford. He's been studying gravity waves in the stratosphere better in order to be able to use machine learning to improve parameterizations in coarse resolution of system models. Right? Yeah, that's right. Please.
Yeah, thanks for the introduction, Ashwin. Hello everyone. I am Aman Gupta, and welcome to the first lecture in a series of 4 lectures on machine learning methods in atmosphere, ocean, and climate science. Just a quick show of hands. How many of you here are familiar with using Python? Oh, okay, good. How many of you have actually worked with machine learning models before? Okay. Oh, this is, I expected more, but okay. Now, how many of you here are computer science graduates or computer science majors? No? Okay. This would be easier than I thought. Okay, so yeah, let's get started. And I'd like to make clear what this lecture series is about to begin with. So this lecture series is an introductory discussion on how to use deep learning algorithms in and how to implement them in Python. This is not, we won't go into details in many places, and we'll focus on developing an intuitive understanding of deep learning rather than going into abstract mathematical definitions. And the goal is to, I would personally be happy and satisfied if all of you walk out with a working knowledge of how to implement machine learning, your own machine learning models in Python. And so it's a series of 4 lectures. In the 4th lecture, we will dive into how ML is being used in climate science, discuss some research, ongoing research, and avenues for future research. Now, what this lecture series is not is, as I said, it's not a comprehensive discussion about the abstract derivations that go behind how to, justifying that your machine learning model is correct and all that. We won't be deploying the ML models we create into complex software architectures. These are simple pieces of code that get you started and can be generalized to more complex problems, but not to industrial scale problems. Now, finally, we will not be creating any, I don't know, maybe I've heard of ChatGPT and DALL-E. We won't be creating those level climate models, not climate models, sorry, machine learning models. But essentially what we learn here do form the building blocks of these more complex ML models. There's a lot more going on there, but still, if you understand this, you will understand that with some more work. Now, just to provide a brief outline of the lecture series, the first lecture, which is this, we will discuss about the parametric estimation problem and how it's related to the whole neural network problem, and how you can go about thinking of neural networks as parametric models. And then we'll go through a introduction to what deep neural networks are and how you can train those neural networks. And in the second lecture, we'll actually do some hands-on coding. We'll look at the Python PyTorch library, which is one of these libraries that you can use to create your own neural nets. And we'll implement our first artificial neural net using PyTorch. Now, the third lecture is a continuation of the second lecture, where we'll implement a different kind of neural net, which is called a convolutional neural net. And we'll implement that in PyTorch. And finally, the 4th lecture, as I mentioned, we will discuss the applications of ML in climate science, discuss some kind of important papers that have been out, some techniques like equation discovery, how they are being used for weather forecasting, how they can be used to create model parameterizations, and so on. Now, just to get the terminology, just to clarify the terminology, you must have heard people kind of interchangeably use the word AI, ML, deep learning, and all. And I mean, maybe you think they are, the same thing. But let me clarify, they are not. I mean, technically, these terms are different. In a sense that AI here, as you can see in this kind of Venn diagram, AI is an encompassing term which encompasses any technology that can mimic human intelligence, like, a robot, or, all these sort of activities. You can, as humans, we can paint a picture of anything. We can differentiate between different organisms, animals. We can create a song, we can write a novel. So any technology that can do that, like, that would be classified as artificial intelligence as long as it's data driven. Now, a subset of artificial intelligence is machine learning, which is a set of all the techniques that you use to empower all these AI tools in the dark blue region, right? So essentially, machine learning consists of all the techniques that consume data, and then they learn from the data, and then they learn to perform some task that we can do or we can not do. Now, yet another subset of machine learning is deep learning, which is what the focus of this lecture series is. So deep learning is a special subclass of all the machine learning algorithms, and they fall under the category of something called as supervised learning, where you train the model on some data and you train the data and you map it to some output label, and then you learn or you teach it to make predictions by feeding it large amounts of data. Now, let's hear from someone you might know. We'll see a video here.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, Killmonger was right, or Ben Carson is in the sunken place, or, how about this, simply, President Trump is a
Okay, let's leave it at that. We don't need to know what comes next. But so you see that video that we just saw was created by a machine learning algorithm. Obama never really said those words. But we are kind of heading towards a future where these things might be common. People can simply create these videos that are called deep fake and can make anyone seem like they're saying anything. And I mean, these machine learning models are the technology, kind of the technical expertise that goes into making these models. So now let's play a little game. Again, a show of hands. One of these images is AI generated and one of these is not. Can you guess which one is and which one is not? Well, okay, how many of you think the first one is real? Okay, I see more and more hands up. Okay, so the rest think the second one is real. Okay, yeah, so the second one is indeed real, but close call, right? And then again, let's take another example. Which of these images do you think is real? Hands up for the second one. If you think the second one is real. Okay, I got you. No, yeah, the second one is actually real, but I guess most people thought the first one is real. Tricky, right? I mean, the models are getting better and better these days in creating all these kind of fake digital content, which even we as humans cannot distinguish at times. Now, this is not it. I mean, you can imagine new scenarios. For instance, image generating model was asked to generate characters from Ramayana, and it generated something like this, which, I mean, I believe that, it was created by a human and looks quite realistic. I mean, with all the ornaments and everything, that's how the TV shows also portray them, right? And then secondly, the same software was used to generate or imagine a snowy winter in Delhi. It doesn't snow in Delhi, right? But what would it look like if it actually snowed in Delhi? So this is what it popped out. So, I mean, we are, what AI can do these days is impressive. So we'll kind of look at some of the techniques the fundamental techniques that power models that can actually do this kind of stuff. Now, don't worry, because the same AI model kind of created this really lame image of 3 people sitting on a couch, like 2 melted faces. Doesn't really make sense. So it's a mix. You can take what you want to from it. Now, quickly showing an AI timeline of a timeline of AI, development of AI. Now, AI became popular, or it was first introduced in the 1950s when Alan Turing proposed the Turing test as a test of quantifying if you're talking to an actual human, like if you're interacting with a bot, what is the chance of it being actually a human? And then after that, in the next decade, there were a couple of AI bots like Unimate, Eliza, Shaky, and so on. Now, okay, interestingly, so when I was a kid, my dad, a floppy disk that had like 1.44 megabytes of memory. So my dad got me Eliza, and I was a small kid, and then I chatted with, it was a chat bot, and I chatted with it, and it was like, I didn't think it was anything special. But then now that I realized that that bot was actually created in 1964, and it could actually, generate perfect responses to my prompts, is kind of impressive. Now, after 66, there was kind of an AI winter where most of the development in new AI technologies and tools halted for almost 3 decades. But after that AI winter, you see development of all these, fancy products and computers that are powered by AI. For instance, Deep Blue. I don't know many of them personally, but yeah, like you must be knowing Roomba. It's like automatic vacuum cleaner. Then IBM Watson, Apple's Siri, then Alexa from Amazon, then AlphaGo, which can play chess and Go and beat humans at the game. Now, AI is driven by advances in machine learning and deep learning. So to give you a timeline of advances in deep learning in particular, again, you could see that the neural net term was coined in 1941, but then the first perceptrons, which we'll see what they are in a moment, they were introduced in 1958. And then there are many terms here. We don't have to go into details of these terms, but then, the back propagation algorithm, which we learn about, was created in 1974. And then the idea of perceptron was extended to creating a multi-layer perceptron, which is kind of the kind of neural networks we see these days. They are one or the other variation of multi-layer perceptrons. And then they were recurrent neural networks, and then they were image recognition algorithms, and LSTMs for time series forecasting, and so on. And more recently, transformers. So you see that there has been a consistent advancement in deep learning algorithms, and the more advancements we make in deep learning, the more or the better AI products we create. So machine learning can be broadly classified into 2 different categories. You must hear different kind of methods, but then they can broadly be, you can understand them as being either unsupervised learning. And in fact, I'm sure most of you here are familiar with some of these techniques, like principal component analyses, k-means clustering for clustering data into different partitions, Gaussian mixing models for probability density estimation, SVD decomposition, Bayesian inference to infer posterior distributions, and GANs. These are relatively new, but then these all comprise unsupervised learning. So they are not all that new. We have used them in one form or the other in our research. And then there is supervised learning, which consists of all these different algorithms like logistic regression, which is used for classification, and artificial neural nets, convolutional neural nets, recurrent neural nets, support vector machines. So support vector machines is something that powers your spam filter in your mail. They have a high classification accuracy. And then you have convolutional recurrent neural nets as well, which is a combination of CNNs and RNNs. And then you have different kinds of RNNs, LSTMs, GRUs, reservoir computing. So yeah, these are, I don't want to overwhelm you with all these words, but then I want to classify all these techniques into like broad classes so that, the key difference between these 2 classes is in unsupervised learning, you just feed the data into the system and you let it do its thing. You don't have to tell it what to do. You can just give it the data and then you can, run the algorithm to separate the data into different clusters. But then in supervised learning, on the contrary, you feed in the data and then you apply a label to the data. So like image recognition, you put in a 7, an image of a 7, and then you tell it that it's a 7. And then you hope that with more and more data, it will learn that it's a 7. So that it could generalize to more cryptic texts and, learn more complex handwritten digits or, stuff like that. Now, more recently, there's an emergence of another class of machine learning methods called semi-supervised learning, which borrow ideas from both supervised learning and unsupervised learning. And we'll see some of it in lecture 4, where we discuss this thing called forecast net, and we'll see how it uses ideas from both supervised and unsupervised learning. And there's another branch of machine learning called reinforcement learning. I'm sure most of you have heard of it. It's used to create bots that can play certain games like chess, Go, Pac-Man, Minecraft, and all that. But it's slightly different. The approach is slightly different from these different classes, like unsupervised learning and supervised learning. So let's dive into it and see what deep learning is about. So consider a very simple problem, that of linear regression. Now, suppose you have this data, an independent variable x, a dependent variable y, then you have this kind of a scatter for your data. Now, just by looking at it, you can see that a good approximation to this data scatter would be a line. So you create a model, you create a linear fit, which looks something like this, y equal to mx plus c. You know x, you know y. So all you have to do is estimate m and c. So you can define a kind of error, like a mean square error, as in this case. And then you can, find m and c that optimize or minimize this error. Now that gives you, okay, for this simple example, you can derive a closed form solution for m and c. Even in multiple dimensions for linear regression, you can derive closed form solution for m and c. But that's not always so simple. Suppose the data is more complex, like a 10th order polynomial you think might be the best approximation. Then you can't really, solve all these by hand or so easily. So then you have to use more complex algorithms, like, create normal equations, create a van der Waals matrix, you solve them efficiently, solve these large matrices using state-of-the-art algorithms and so on. Now, similarly, let's look at another problem, that of maximum likelihood estimation. So suppose you have a data and you look at its distribution. So say what we see here in green, say the empirical distribution looks something like as shown in green, okay? Now, your objective, or what you want to do, is get an analytical form of a parametric distribution that best approximates this data. So again, you start with some kind of a, prior distribution. You assume a prior distribution, which in this case, if I tell you it's a Gaussian, you will say, no, it cannot be a Gaussian because it's visibly asymmetric. So, you will choose your parametric distribution intelligently. So in this case, log normal could be a good candidate. So you start with log normal distribution, you have your data x, and then you solve this optimization problem however way you want, right, to get theta MLE. And that uniquely defines your distribution that best fits the data according to some error bar or error criteria. Now again, the theta, optimal theta you get is determined by the distribution, the prior distribution you assume would be a good fit for the data, and then also on the algorithm that you use to solve the parameters, right? But the main point is you have boiled down this problem into a parametric estimation problem, just like the linear regression or multiple regression problem. Now, deep learning is somewhat similar. So let's look at perceptrons. Now, perceptrons are like the building blocks of modern neural nets. So, I don't know if they use this term. I thought it would be good to just call them atoms of deep neural networks. But say you go to a neuroscientist and you ask him how our brains work. Now, brains are made of neurons, right? So a simple model of how a neuron works or how we think could be that a neuron gets inputs from all these dendrites, and then it outputs. So these are electric signals. It gets some incoming electric signals from different dendrites, maybe not all, some dendrites, and then it passes it through the backbone of the neuron. And then accordingly, depending on what information it has, what all dendrites are activated, it will pass a certain output. So that could be either activating further neurons or not activating any neurons after this at all, right? Now let's create a simple mathematical model of this. So what you see here would be a simple schematic of how a neuron might learn. So what you see here in blue is the dendrites, different branches bringing in information to the neuron. And then what you see here in green is a weighted average or a weighted sum of all the information from different dendrites. Now you take this weighted sum, and then now the magic of all this is this nonlinear activation, because otherwise it's just a linear system with limited capacity to predict, right? So let's imagine a simple Heaviside function as this nonlinear activation function, where if your weighted average is above a certain threshold, your output is 1, which means fire the next neurons, send a electric signal to the next neurons in the network. Or if it's below that threshold, then do nothing, okay? So this kind of a simple mathematical model was first developed in 1950s by Rosenblatt. It was called a perceptron. Now, our brains are complex, and depending on what you see, you might or might not, like different parts of our brain control different activities, like visual cortex, your audio is handled by a different part of the brain, and so on. When you dream, your different part of your brain is fired. So similarly, when you see a cat or a dog, a different part of your brain will be fired, and it's like the information pathways that are followed in your brain to help you determine what kind of animal it is. I mean, it works in a similar way. Now, again, what we have done is take this neuron and understand how it works and create a parametric estimation problem, because how well you, or what output this model generates is dependent on the weights and how well you can estimate these weights. And that depends on what data you input it and how you train it, okay? Now, the key component of this model would be input, whatever input you plug in, the weights, Wi is here, the Heaviside function, the nonlinear activation function here, and the output, which is what output you get based on what input you fed into the model. Now, a neural network in general is a collection of many of these perceptrons, because we don't have a single neuron, but perceptron models a neuron. So when you put together many of these perceptrons, you kind of get something like this. I mean, you can put them however way you want. You can essentially make a graph of these perceptrons, looping or non-looping, but you can arrange them in a fashion like this, where this is your first layer, this is your input layer. Your information into the system is fed through this input layer, and then it propagates the information from this first layer to the second layer by communicating this input xi through to the next layer using a system of weights W1. Okay. Similarly, this would be your input layer, this green would be your output layer, and these two would be your hidden layers. Okay. Similarly, you have so your information propagates from your second layer, that is the first hidden layer, to the second hidden layer using a set of weights W2. And once you apply this affine transformation W1 x1, then before you actually set the values for the nodes, you have an activation function sigma that operates on your data. Okay, so essentially this kind of a network is called a feed-forward neural network, and this propagation of system from one end of the network to the other end is called forward propagation. Okay, yeah, essentially, say you have one input, then your information might propagate in one way. I mean, it's not necessary that all weights would be non-zero. Sometimes the weight could be zero, which means they don't propagate any information. So and again, so when you collect many of these perceptrons in a certain way where your information is propagating just from left to right as arranged here, and your activations for all the layers is identical, then you get something which is called a feed-forward neural network. Okay, but then you can ideally have different activations at different levels. You can have different sizes for different levels, and so on. This is a lot of freedom of what architecture you go for. Now let's look at some results from theoretical machine learning, which comment on the learning capabilities of these neural networks. So if you just consider a perceptron, a simple perceptron, then I mean, this result goes back to 1969, that these single layer perceptrons can only learn linearly separable patterns. So what do you mean by that? So just take an example. So you have different Boolean functions like an and function, or function, exclusive or, exclusive and. So and or are linearly separable functions, but then an exclusive or function is not. So a single layer perceptron is incapable of actually modeling that simple of a function. But then if you develop a multi-layer perceptron by putting together multiple perceptrons, they are much more capable of learning any possible Boolean function. But then can they learn any possible nonlinear function? So that is governed by another theorem, which is called the universal approximation theorem, which is central to the theory of machine learning, which says that given any continuous function in an n-dimensional space whose domain is 0 to 1, and it pops out value, like its range is from 0 to 1 as well, it can be very well approximated by a neural net with at least one hidden layer. You need some hidden layer, and you don't have to have infinite learning capacity. You can have a finite number of weights, and it will model that. It should be able to model that. The only caveat is it does not tell you how construct such a function. It just tells you there exists a neural net. So, we have to kind of go through the hard work ourselves to determine what that neural net is. But so here's an example of a deep neural net that does or performs handwriting recognition. So can you all see this? Sorry, it's a bit blurred. But so this animation here is showing what a vanilla artificial neural net does. So what you're doing is you have an image, you take that, you transform it somehow into a vector. We'll see this, okay, in the next set of lectures. You transform it into a vector, and then you pass it through this deep neural net. And then, so this is the final layer, which has 0, 1, 2, 3, 4, 5, 6, 7, 9, 10 classes, okay? 10 classes of numbers. And then you train this, and you can see that the yellow is kind of, okay, it's a schematic, okay? It shows the yellow, the information propagation in yellow color. So you see that you input an image, and after you go through the training process, it can actually guess what the number is. So this basic artificial neural net can be used to construct more complex neural nets as well. So just an example here, this ANN can be used to construct convolutional neural nets, which are used for image recognition and other classification tasks. So there you have an image, and then you go to the image in a certain linear fashion using something called as convolutions. And then it creates a simplified form of an image, and then you use that simplified form to train your neural net to learn to identify that image. I won't go into much detail into this now, but we will revisit them, okay? Similarly, you can have another class of neural nets called recurrent neural nets that are popularly used for sequence modeling, like time series forecasting and so on, which is essentially you take this ANN and you put 10 such identical ANNs, one feeding into the other, and that learns to generate autoregressive processes and complex nonlinear systems, such. So let's see how to train a model. So as I mentioned, the crux of machine learning would be you give it some data, you have some you map that input to some certain output, and you expect your objective is to learn the weights optimally of these feed forward neural networks. So how do you do that? Okay, now, okay, what's this? Okay, yeah. So the algorithm to actually learn and update the weights can be briefly or discretely written as a series of 5 steps. So the first step would be define your neural net, define the weights, define the sizes of different layers, and then initialize those layers with some small random value. I mean, there are strategies how to initialize your neural nets, but any initial random initialization from a uniform distribution will work well as well. Then the second is the forward pass, which we just saw a couple of slides back. You have your data, you input the data from the first input layer, and then you then propagate that information through all the different layers, all the way until it makes the prediction in the output layer. Okay, and then the input is also called features in ML lingo. The next step is to test if your neural net actually predicted something meaningful or if it was totally wrong, right? So so how do you do that? You quantify that using a loss function or an error function, which could be, we'll look at different kind of loss functions tomorrow, but then it could be as simple as a least square, a Euclidean measure of Euclidean distance between 2 vectors, okay? And then now that you know how much error there is in the prediction, you back propagate your error all the way from the final output node to the previous layers, all the way to the input node. And this back propagation algorithm is sort of the magic behind all this. So once you go through this backward pass using this algorithm called this back propagation algorithm, you update the weights using some kind of an optimization scheme that updates your weights depending on what error you had in your prediction or how much error the model made in its prediction. Okay, and then finally you use that knowledge to update the weights. Yeah. So how much time do you have? 15 minutes? Okay, not bad. So you iteratively do this for a certain number of iterations, which you can choose. Okay, there are methods to determine what the optimal number of steps is, but then yeah, we'll look at this into more detail, but then you can choose how many time steps you want to iterate this whole procedure, step 1 to step 5 for, and ultimately, when you're happy, when your error is below a certain threshold, or when your predictive skill is above a certain limit, then you can stop. Okay. Now this is the training phase. All these steps define the training phase of your ML, but you want to use the ML for a specific problem, right? So then comes the inference step. Then you just use the model for evaluation and testing, and you can revisit the training algorithm again as well. It's not a one-time thing. So now let's look at each of these steps and see what's actually going on behind each of these steps. Okay, so we don't have to assume a very complex neural net to understand this. We'll just take this set of 2 perceptrons connected linearly one after the other and see if you can make sense of what's going on. Okay, so imagine you have input xi's and then you have output yi. So these are truth that you know with certainty. You know, your objective is to determine what W1 and W2 is. So you design a simple neural net with an input node with value x, and then you have a hidden node with value h, and then you have a prediction output node which makes a prediction by p. So you have 2 weights, and then once you have a mapping, this linear mapping of multiplying the input or the value of a previous node with the weights, you apply a nonlinear activation using an activation function, which I've assumed to be identical in this case, sigma. Okay. Just so that you have an idea, sigma could be anything simple like a sigmoid function, which is used for a binary classification. Okay. So this is I think this is 0, and this asymptote here is 1, or it could be something else like a tan H function, or so just think of this. Okay, it's like a continuous approximation to a Heaviside function with more flexibility here. So when we look at what properties these activation functions have and how you can ideally construct your own activation function as well. But let's for now consider this simple neural net with 3 nodes. Okay, so what's happening is you put in so step 1 is you put in the input. So what's happening is you have this input x, and you're multiplying it by the weight W1, and then you are passing it through the activation function that gives you sigma of W1x. You call this h, okay, the value at the hidden node. Now, subsequently, you multiply this value h with W2, and that's W2 times sigma W1x, because h is sigma of W1x, right? So now you have some value which you again pass through the second activation function sigma, and then this gives you the value at the output node. So your yp can be written as a function of wi's through this sequence of functional operations. So you're compositing operations one by one as you go from the input layer all the way to the output layer. Now step 3 is, again, as we discussed, you have made a prediction, you want to quantify how good that is. So you need a measure of that, you need a way to quantify that. So you choose the loss function, which is dependent on the truth y, the prediction by p, so that it can compute the distance between these two. And then of course it's implicitly a function of the input x, w1 and w2. Okay, now let's define it to be a function L tilde, which is only a function of yp. Okay, so that's step 3. Now step 4 would be computing the derivative. Well, actually I don't remember what step 4 was exactly. I think it's backpropagation, right? Yeah, step 4 is backpropagation. Okay. So now to update your weights, now the loss quantifies the error in your prediction, right? So you want to kind of do something with it to update the weights so that next time it gives you a better prediction. It's an iterative process, right? So now, I mean, if you know this from basic calculus, that if you have a function, a multivariable function, then the direction in which the function increases the most or changes the most is its gradient, right? So suppose you look at the loss function, if you look at its landscape in the weight space, so loss as a function of the weights w1 and w2, it could be complex. Like as you have more and more weights, it could be very complex of a function. So you want to find a way to update your weights by using the loss and its gradient to update and get to a better set of weights. So to do that, you can apply a very simple approach, which is called a gradient descent, which is move certain amounts of steps in the direction of the maximum gradient. Okay, and you can choose how big of your step you take. But the catch here is that to do that, you need to compute the gradient of the loss function with respect to each of the weights so that you can get better weights, right? So for this model, it's probably not that difficult. But then, all these big neural nets have billions and billions of parameters. So it's not so easy to, like a brute force naive approach would be to simply perturb your weights a bit, W1 minus epsilon, W1 plus epsilon, and then look at what the output is then for this model. But then doing this for many weights is not very trivial and is very time consuming and inefficient. So we need a better way to do this. Now let's see if we can, with this simple problem, compute what the gradients of the loss function with respect to the weights are. Okay, so assume a generic function L. You want to compute its derivative with respect to the weight 1. Implicitly, yp is a function of y1, w1 and w2 because you use those weights to obtain the prediction yp. So you compute that, you try to compute the partial derivative, and you get a total derivative of L tilde, which is its derivative with respect to yp. And then you use chain rule then, because then you use a sigma to get that, right? And yp is essentially this expression. So you plug that back in, you get another derivative term that's d sigma over dw2. And then again, you go on and on. Sigma is itself dependent on w1 and w2, as in the argument within sigma. And then you go on and on till you reach the independent variable x, x or w1 or w2. So computing this simple derivative, it's partial. I'm sorry, we are computing this derivative first because it's closer to the output node. Okay, I'm sorry, I misspoke. But this partial L, we compute partial L tilde, partial L2 first. And then once you apply this chain rule, go back and back and back, you get this as your gradient of L with respect to W2. Now this is complex enough, but then next we'll compute the derivative with respect to W1. And then you see that, you need more operations, apply a chain rule deeper and deeper, and then you get this expression as the derivative of the loss function with respect to W1. But then one thing that we notice here is that this expression is identical to this expression. And then this term here is the only new term, I mean, apart from h and x. Okay, so this gives you a slight intuition into what backpropagation could be like. You first compute the gradient for W2, and then you can reuse that gradient to compute the gradient of the loss function with respect to weight W1, because you have already computed these two terms. Okay, so now what we are approaching is towards a recursive explanation or recursive description of the backpropagation algorithm. This brings us to step 4. Okay, so we propagated, we had the forward pass in step 2, and now we first compute these errors at these different nodes. Okay, so delta 3 is the error at node 3, delta 2 is the error at node 2, delta 1 is your error at node 1. But because you know your input with certainty, your delta 1 is equal to 0. Okay, so only these and these quantities are non-zero. Now you do a backward pass using backpropagation algorithm. How do we do that then? So you saw these complex expressions for the gradient, right? Now, the backpropagation algorithm suggests that you don't have to compute these gradients all the time. You can use ideas from dynamic programming to do that for you. So what you do here is, imagine a general neural net. You compute these delta terms, the errors at different nodes. So you define sigma at the final node to be L tilde prime sigma prime. Sigma is the activation function, and in general, you know the closed form of your activation function. So you know sigma prime as well, and you know the analytical form for L tilde. So you know L tilde as well. Okay, so you compute that, and then you use this iterative relationship to compute the error at all the nodes preceding this output node. And then that's one step. That's one sub-step of the backpropagation step, where you first define the error nodes at each of these steps, at each of these layers. Now, the next step is computing the derivative, using this information, the error nodes, to compute the derivative. Now, you have computed delta L at each layer, right? So now AL is the value, okay? I'm sorry, I don't mention it in the slides, but AL is the value at these nodes. So it's YP here and H for this node. So you take the value at a given node, you compute the delta, or you use the delta at the next node. So this would be taking H in the second node, using delta 3, and then using sigma prime, according to this expression, and multiplying it to get the derivative of L tilde with respect to W2. And then again, you do that, and then once you have that, you go back to the first layer, and then you compute this expression for this layer as well to get your derivative with respect to W1. So this is much easier to compute than actually computing the derivative for billions and billions of parameters, okay? And then once you have the derivative, you take this optimizer step. That is, you move in the direction of the gradient at a given step using, and the given step here is denoted as alpha. I don't know why it is so blurred. Can people follow? Okay, the slides will be available, so I'm really sorry. It shows clearly here. But yeah, and then so this constant here is called the learning rate, which is the step size you take to update your weights, and you can adjust that. And the training process consists a number of these constants, and together these constants are called hyperparameters of your model. Okay, sounds like a fancy term, but it's just a set of constants that you decide. Now, finally, I'm towards the end now. So with this, we are pretty much ready to create our own neural network. I don't know if it feels like that or not, but you'll see, you don't have to bother with all these details of the backpropagation algorithm, because as we'll see tomorrow, PyTorch has its own implementation of dealing with this. So you don't have to really care about all the dirty laundry, so to say. So you don't have to deal with it. You can just have a high level code, and those high level functions that you use implicitly call the backpropagation functions and all these complex functions, and you don't have to worry about computing the derivative yourself. So essentially then the 5-step process now seems much simpler than what it would be if you have to compute the derivatives yourself. So just to summarize, we looked at the broad definition of machine learning, and one key takeaway would be that machine learning techniques would be broadly divided into 2 broad classes: supervised learning and unsupervised learning. In supervised learning, you give the model an input, and then you match it to a certain label output, which you know in advance. And in unsupervised learning, you feed in a data to a given algorithm, and then you let it detect, things like anomaly or clusters or patterns in your data, or reduce variance or get a lower dimensional approximation to your data. So we looked at neural networks. We defined neural networks using perceptrons, the building blocks of deep learning models. And essentially, they are a set of different layers, input layers, hidden layers, and weights and activation functions. And ultimately, the main objective of having a neural net and training it and using it for any application is to estimate those weights as optimally as you can. In a sense, it's a parametric estimation problem then, just a different scenario. And then the optimal way to train it would be to iteratively feed in the data and then optimize your weights using the backpropagation algorithm, and then update them until they reach a certain threshold. So yeah, I'll take questions now, but okay, I just have one small announcement. So for tomorrow's lecture, I mean, it would be great if you can have a PyTorch, have the PyTorch library and a Jupyter notebook set up on your laptop. So I don't know how many of you use Windows, but then for Linux and Mac, they should be straightforward. I usually use it works. I use Conda usually. You can use pip as well. There are different package managers. So you can use Conda. And if you have not used Conda before, you can actually go simply Google Conda, and it lets you download a script, and then you can just do a sh command and run that script, and it installs Conda. So once you have done that, you can do all these Conda commands that directly install all these different packages for you on your laptop. Again, I'm not sure how to do it on Windows. I guess Windows does have a terminal shell now, right? So you should be able to use the exact same commands. So you can install Jupyter Notebook like this. You can install NumPy and Matplotlib like this. NumPy is a numerical computation library of Python. Matplotlib is a plotting library with all these functions that were previously in MATLAB, now can be easily used in Python. And then finally, it would be great if you can install PyTorch, which is the library which has all these inbuilt functions and classes that can help you to compute the neural networks with ease and convenience. And then the way to do this is go to the PyTorch website, choose a certain configuration, stable, of course we want stable, Linux or Windows, Conda or different package softwares, package managers, and then language, which would be Python in this case, I hope. And then if you want CUDA support or not, depending on if you want to run your neural nets on GPUs or not. I don't have a GPU on my computer, so for me, but it's good to install it with CUDA, just better. So it will pop out a command that you can then use to download your PyTorch on your laptop. Okay, so that's pretty much it. Thanks. Okay.
Questions?
Hi, thank you for the talk. My question is, when you actually initialize your weights, like how do you choose your weights? Like when you're initializing, like is it just random, or like is it problem specific, or?
It could be problem specific, but then random weight initialization works as good as any other. The only thing I would say is don't set them to 0, because your update process could be slow, and that randomness helps your gradient update method to actually update your weights faster and more optimally.
Thank you.
But you can sample from any distribution, a uniform distribution with a small range, or a uniform distribution, or a Gaussian distribution with a certain small mean and variance.
Hello, sir. I wanted to ask you, whenever you are working on a specific problem and using AI or ML to improve something, for example, forecast, right? Do you simultaneously also look at interpreting the layers that you've built, like how exactly it's improving it? Because it's important to understand what's going on, right? You can't just trust the output that your model is giving. Yeah.
That's a valid concern, and that's a big problem in the ML community right now. I mean, how do you interpret the result that you got? How can you actually deduce how the model arrived at the conclusion or the result it generated? And ideally, yes. And I mean, if you work with models like convolutional networks, then there are ways of interpreting what's going on in each layer, and we will see glimpses of it in the next set of lectures. On Thursday, I think we'll do convolutional networks. So there, it's because it's all visual, it's easier to see what's going on. But no, I totally agree. It might not always be possible for more complex networks. Sometimes it works in terms of probability distribution. So you can't always interpret your results. But yeah, there are ongoing efforts that are creating tools and techniques to interpret your results better.
But do you think this way you can kind of isolate what's going on, like the physics of it? Do you think that's even possible?
You mean physics of neural nets?
No, like how it's able to improve something from interpreting the layers. Do you think you can understand the underlying physics? Like, has this ever been done before?
I don't think there is a general answer to this. It can depend. Some people, like some research groups, are actually looking at images of, say, global temperature rise outputs from different models. They're trying to interpret what patterns are actually the neural net is catching or targeting to learn what the temperature in 100 years later would be based on global temperature rise from 1979 or to all the way to 2050. So like you train it on 70, 80 years, and then you ask what the temperature would be like 200 years from now. And using some interpretability tools, you can do that. But no, I don't think there's a general answer to that.
Yes,
I mean, you
thank
can always track the flow of information, but then that won't help you interpret everything. So,
Thank you, sir.
Rather than understanding the layers, would it be useful to look at which of the features are more important, like in explainable AI?
Yeah. I mean, there are tools. There's a tool called Shapley values, which allows you to play around with the feature set you put into the model, and based on that, you can actually score each of these different features. Like if you are predicting some atmospheric phenomena and you put in horizontal a zonal wind and your meridional wind, it's possible that the meridional wind does not contribute at all in determining the output. It's only the zonal wind. But yeah, so you can kind of have these metrics that allow you to see the importance of different features. But again, there is this problem that, I mean, when you're training, I wouldn't recommend, or people don't recommend, putting more weights to different features, because that's kind of, you just want to let the machine learning model do that by itself, rather than telling it that, oh, look, give more weight to the zonal wind than the meridional wind. It's more like a diagnostic process rather than a prognostic process.
But at initial level, we have to give some weight.
Yeah, and that depends on your intuition and your understanding of the problem. So yeah, it's possible that you don't have the all the features that define the problem, and yeah, it's kind of a iterative process. So what people usually do is take a more overarching, like a superset of all the variables that they think would be needed, and then cut features one by one. Yeah, you can draw an analogy. Yeah.
Same thing for back propagation. So it is somewhat like bias correction that you do in models. Is it somewhat similar to that?
Bias correction. Not sure. It's not clicking. What bias correction?
Do bias correction. So is back propagation somewhat similar to that?
I don't know. I have to see how the bias correction is done. Like climate models, you mean? So I think it would be different. I'm not sure. This is more like a gradient computing process, back propagation. So that's more like in the realm of computational mathematics than in climate science. I don't know. I don't think I have to look what they do for bias correction.
Yeah, just a follow-up question here. Just a follow-up question from before. Do we get to know what each node is learning? Like, is it even beneficial to get to know that? What within layer, what each node is learning? Is it important to get to know that?
Yeah, I mean, the more information, the better, right? And and you can actually do that. I mean, once you have trained the model, you can look into the weights and you can see what the sizes of the weights are. And like for convolutional convolutional neural nets, you can actually go back and look at the filters that it learned that extract all the features from your image in general. And yeah, I think that helps.
Okay. And there was mention of grid search, but grid search of like what, like different variables? What, there was a mention of grid search, right? In one of the slides.
Grid cells where?
I forgot the slide number actually. To find the optimum.
You mean step size?
No, grid search, like.
Grid search,
Yeah.
okay. Oh, I guess grid search it's just a popular algorithm. Like if you have a parametric space, W1, W2, then you just take a W1 from 0 to 1 and W2 from 0 to 1, and then you just search that space one by one, and you compute the loss function and see what it looks like, and then you manually pinpoint the minima. So that's what I meant by grid search.
Like we are doing it at that for weights.
Yes, for weights, yeah. But I mean, I'm sure it can be used. It's not just restricted to machine learning, it can be used anywhere, right?
All right, thank you.
Question? Anyone else? Yeah. Okay, there's a question here, a question there. Okay, maybe two more questions.
Yeah. Thanks, Aman. One question, like how you decide how many nodes you would have in that each layer, and how many hidden layer we will have?
Yeah, that's a good question. Usually, I mean, when I started coding neural nets, I played around with different node sizes, different widths of each layer. And then I think the general consensus is start with a simple model. Now, we looked at the ML theorems, right? It says that it's good to have one hidden layer at least. So that's like an obvious answer. It's good to start with at least 2 or 3 hidden layers and then move your way up. Because the more layers you have and the more nodes you have within each layer, the more data you need to train the model optimally. And in practice, usually, even if you have 2 or 3 layers with, I rather not comment on the width, but if you have 2 or 3 layers, then they are sufficient to capture many nonlinear functions. So a good strategy would be to start with a limited number of layers that you can handle and interpret properly, and then move over to bigger. If you think, if you're looking at the loss curve and you think that the model is just not learning, because the more layers you have, the more is the learning capacity of your model, but then the more complicated is the training process. So we'll see this in convolutional layer. So suppose you have an image detection algorithm that detects human faces. So it's possible that if you have 3 layers, then the first layer might detect a round face, that humans have a round face, and maybe something like this. But the second layer might detect small scale features like eyes, and nose. So it's like the more layers you have, the more small scale features you can detect. But then again, it doesn't mean that you should start with 20 layers. Start with 4 or 5 layers and then see how your loss evolves.
I have a question which is sort of linked to the question that was just asked. So is the number of perceptrons linking the input to output, is it constant or can it change dynamically? Like, is the number of layers always a constant that you predetermine? Like you already design it to have 2-3 layers, or can it dynamically change to have more layers?
No, I mean, it's a hyperparameter. So it's up to you to decide how many layers you want, and how many perceptrons should be, how many nodes should be in each layer. But yeah, I think as I said, the more layers you have, the more features you can detect in a broad sense. And then the wider each layer is, the more memory sort of your neural net has. So there's always a trade-off. So it's like, I mean, do I have time? Like 2 or 3 minutes? Okay, I'll just quickly explain this. So, suppose your neural net, I'll just write here. Suppose your neural net has, suppose the depth of your neural net is D, and then your width is W, right? So the number of, assuming a square weight, then your number of parameters are order W squared D, right? So if you want to constrain the number of weights in total for a neural net, then it's usually recommended to increase the depth of a neural net, because if you increase because it's squared, right? So it's like if it's 100, so if it's 10, if you have 100 weights, then and if you have a depth 10, if you have a depth, okay, I'm not doing a good job at explaining this, but it's like if you want to double the depth of your neural net, you will have to what is it? Sorry, I mean, do you see this? It's like if your number of weights are fixed, then you would have more gains by changing D by a factor, but then your weights will only change by a factor of square root of that factor. So it's usually recommended to change the depth size than the width. in general. Yeah, thank you. There is one, I think. Sorry, I'm not able to see this. Explainable AI. Can you elaborate, please? But I guess that relates to the question you asked, I think, right? Can you interpret what you're getting? So, I mean, explainable AI is, yeah.
No, that part is from the earlier interaction only.
So should I go to the slides?
You had answered like Shapley values and all that.
Oh, okay, I did. Okay, thanks.
Okay, thank you very much. Let's thank our speaker, and we'll reconvene in less than 15 minutes in time for the next speaker at 4.